All right, and we're live. Today, Precalculus, we are looking at transformations. We have looked at all the parent functions, all right, and our goal, our ultimate goal, is to be able to graph anything. All right, if I give you x squared right now, you know that's a parabola. But what if I give you 2x squared plus 5? What is that going to look like? That's our goal, and that's kind of the question we're going to address today. How do I graph transformations on parent functions? To do that, we're going to graph this made-up parent function. One of my favorite functions. Cha-ching. This is the check function. Why do I call it the check function? Ms. Contreras, help me graph this thing.
So let's plug in our endpoints. -4, 0. Negative, -4, -4, 0. Oh, wow, we're using blue.
It's blue, okay? I
Wild.
love blue. Blue's nice.
Wow.
I can go back to pink.
Nah, it's
Not
cool.
Wednesday.
This is a very like Grover kind of blue.
Ooh,
Nice.
Grover. Nice
Yeah.
reference. Get some Sesame Street in here. I like it. Okay.
And it's a line, right? So we just need to plug in the other endpoint. So -2 is +2 -4, -2. -2, -2. And then plug in -2 and we get -3 + 1, -2. So we still have a continue, or we have like the same point. So we're good.
Yeah, if we didn't, we'd just plot it somewhere else.
Yeah.
All right, but we'd put a
open
hole wherever that thing is because there's no equal sign. But
Right.
alas, we do not have that. It is in the same spot. This is continuous. Let's continue.
Continuous.
No pun
Let's
intended.
continue. So let's plug in the other endpoint. 2 times 3/2 is 3, + 1 is 4. So 2, 4.
Nice. And here we go. And I'm going to be really careful here because this will matter later in terms of transformations. We've got a slope of 3/2. So 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. Okay, so it's consistent. But notice I'm not going through -1, 0. What is that point? What is that x-intercept right there?
X-intercept, -2/3.
Yeah, -2/3 is it. All right, and if you don't believe us, that is not a 3. If you don't believe us, just solve that second equation for 0, right? Yeah, because a y needs to be 0. Boom. Cool. So that's not necessarily important right now, but let's keep that in our back pocket. All right, we got the check function. That's why I call it the check function. It looks like a check. Excellent. All right, so we want to see how this function transforms as we alter it in some way. But before we, never mind. Let's see what this +5 does to our function. So we could just plug things in. Let's not do that. What is this saying?
That's saying that we have our check. We have our check like this. Our check. How about that? We have our check. And then we are increasing each of our outputs by 5.
So over here, I got the output here is 0. So the output over here at -4 is going to be 5, right?
+5, yeah.
The output here is -2, so we're going to be 3, +3.
+3.
Okay. And then that -2, 0, that's going to be -2, 5. 1, 2, 3, 4, 5. I don't really need to graph that point, but it's nice to know where your x-intercepts are. It's not an x-intercept anymore, but. And then 2, 4 becomes 2, 9.
Barely still fits on our graph.
Still fits on our graph. We can always change the scale if that's a problem for us, but we don't need to. And I believe we've crafted this lesson so that nothing goes off the x-axis. Sorry, the window. I don't know why it's an x-axis. The x or y-axis window.
Cartesian plane? Coordinate grid?
Coordinate plane, Cartesian plane. Yeah. All right, so let's decide what this +5. What if I had any number? What if I did like f of x plus k? What is it going to do to the graph?
It would change in the vertical direction what the position is by k. So if k is a positive number, then it would go up by k. And if k is a negative number, then it would go down by k. And if k is 0, then, Doesn't move.
It's not, no transformation. All right, I'm gonna use some geometry terms from last year. Translation.
Ooh.
Ooh, and geometry teachers love SL, slide. Was that the word you used? Maybe not.
I did not.
I think you used a different word, like shift or something. But translation, it's translating. Let me actually say this with proper grammar. Translating up. And I'm gonna write slash down. This one's going up, but that +5, that plus K can do some, whatever its direction is, positive or negative. All right, cool. That's a simple one. These
So it's
will
just
progressively get more difficult.
It's like a regular elevator.
Yeah, a regular elevator, not like Charlie and the Chocolate Factory elevator. This
Crazy
isn't going.
elevators.
No. All right. Now we need to keep this check mark in our brain because we're losing it. But
Okay.
you know what? Actually, I'm gonna go ahead and graph it. This is something that you can do if you are working on a transformation. Put your original, what we call the pre-image, on your graph, and then we're going to. I'll use a different color. I'll use pink, or maybe I'll use red for Elmo. Right? You know, people associate
yellow for Big Bird because it's part B.
Let's see if yellow. It's kind of hard to see. Sorry, Big Bird.
That's tough.
But people associate red with bad, but Elmo is red, and Elmo is like the essence of good. So let's use red, and let's think of it in a positive way. What are we doing?
We are taking all of our outputs and we're multiplying them by 2.
So what's 0 times 2?
0 times 2 is still 0.
Zero product property. -2 times 2?
-4.
-4. 0 times 0, you already told me that was 0.
Still 0.
And then 4 times 2?
4 times 2 is 8.
Boom. And let's get this sketch going. And I do have my line tool. You know, I'm just going to use it because this one right here, that's going to be hard to draw.
That's true.
Where's my line tool? There it is. There it is. Boom. Ooh, but I don't want red.
But it's still blue, Mr. Kirk.
Super Grovers. I can't finish that.
Isn't his outfit like different? Doesn't his outfit changes when he's on Super Grover, right?
I think that he like zooms out of the screen, zooms back, and it's super. I mean, they're different people.
That's the point.
Anyways,
yeah.
There you go. There is our 2. I almost gave away what this transformation is, but what is that 2 doing?
It is. I think it's dilating.
And I'm still in dilating.
It's dilating, and it's dilating vertically, right?
Yeah, vertically. Right, and there's 2 different types of dilations. There's stretching dilations and there's compressing dilations. So let's kind of get that under our belt. Right? If this number, let's not worry about if it's negative or not. All right, that's what the number letter C over here is going to tell us. But if this number, let's call it A f of x. If A is between 0 and 1, what's that doing?
That is going to be a compressing.
A compression. Yeah.
Because whenever you multiply by something that's between 0 and 1, you're getting a smaller number.
X. Right. What if A is, let me write it like this. No, I'm writing it like this. Yeah, what if A is larger than 1?
If A is greater than 1, then you're going to get what we had here, where we have a dilation that's stretching.
Yeah, stretch. All right, so keep an eye out for that, and then there you go. So that is our second transformation. We have translation, and this is non-rigid. It is a dilation by the scale factor that we give you in the front. All right, I think back to geometry. If your dilation factor was negative, it did something. What is this negative?
The sign.
Of all the outputs, right?
Of all the outputs, which means that all the signs for below the x-axis would reflect up, and then all the signs above the x-axis, those would reflect down, so you get the whole check. So which way is the check? You get the whole check, and you reflect it over the x-axis. Is my check in the right direction? Oh, it kind of is. Yeah, hey! I hope it doesn't flip my video.
I don't think it's gonna. I mean, I don't know. I don't know if we've been flipped this entire school year so far. Maybe we should check on that and see. There you go. Yeah, that negative is. Give me the rigid transformation name.
I think it's a reflection over the x-axis.
Yeah, and if you remember, everyone back from geometry, when you describe a transformation, every transformation requires certain things. A translation, they require direction. Reflections, you also need to specify your axis of reflection. So here, Mrs. Contreras has said that it's a x-axis over the x-axis.
Mm-hmm.
Over the x-axis, and then I'm going to add, just so we're internalizing it, that is the line y equals 0. You know, I had someone in calculus today who misinterpreted a problem. They thought y equals 0 was vertical. Right, don't tell them I said that. All right, there you go. Reflection over the x-axis if that negative is in front. Now, I want you to notice something. All three of the problems that we've done here have affected what part of this function, the domain or the range?
They've all affected the range because the domain is staying the same.
-4 to 2, -4 to 2. B here is -4 to 2, and C here is -4 to 2. The domain's not changing.
Mm-hmm.
Oh, but the range is. And that's what something outside of a function does. If you take the outputs, anything that you do to the outside is going to change the range. What do I mean by outside? I mean, I'm going to write it down here just to get your attention. I know you can't see my cursor. Right, I have a function. If I multiply that function by something, or I add something to that function, I'm going to be changing the range. What happens when I do stuff to the inside?
Ooh.
And it's a little bit more complicated, in my opinion. Right? Someone else might say that it's not complicated, but in my opinion, it's a little bit more complicated.
I think it's complicated.
I think so too. It's counterintuitive, and you'll see why in just a second. So I've done everyone a service. If you're following along in physical notes, like I know some of you are, I have gone and put the check mark here for you. And you can, if you want, put the original check mark on each of these graphs to help you. That is something that I've seen over the years people do. We're not going to do that this time. Or maybe we will. I don't know. Let's just see how it goes. All right? Work with whatever you feel in the moment. All right, so we are taking the function that looks like a check mark. And what are we doing to it?
We're subtracting 3 from our inputs.
Okay. So like, so if you're saying, let me just try to understand what you're saying. We're subtracting 3 from the inputs. So the original inputs were from -4 to 2. These were the things that were allowed. So for subtracting things, including. For subtracting from the inputs, then can I plug in -7 and 0? Can I plug those things in?
No, because if you plug in -7, right, you have -7 minus 3, which is -10, and our original check is not defined at f of -10, because that's outside of the domain. So
we're not truly subtracting from the domain. What are we doing? I'm going back here.
Are we adding?
This -3 is deceptively adding to the domain, right? We need the object, we need the expression x minus 3 to ultimately, before the function evaluates it, to be between -4 and 2, right? Yeah, -4 and 2, right? This inequality tells us everything that we need to know. But let's solve it. How do you solve this extended inequality?
Well, first, I think we're missing our greater than or equal to's.
Oh, okay. I will forget those. Now, I like to consider this just like justify myself. I like to consider this just sketch work. As not there's a C in there. Sketch work, right? So I am not going to penalize a student for not throwing those inequalities in there. Mrs. Contreras is bringing up a really good point that we should be careful and we should mean what we write and write what we mean. So you know what? Yeah, you know what? I've changed my mind. Yell at me if I don't put those equal signs because they should be there. You're right.
Boom.
All right, so let's solve this extended inequality.
All right, so I think we need to add 3 everywhere. So then we get -1 is less than or equal to x, which is less than or equal to 5.
That's the new domain. So those are the values that we can plug into D. When we plug 5 into D, then F takes that number 5, subtracts 3 from it, gives us f of 2. And then we can go back to our original function and remember what f of 2 is, which is right here, 4. So 5 out of 4.
So it's moved to the right 3 units.
So we were at -4 zeros. Now we're going to be at -1 0. We had -2, -2. Now we're going to be at 1, -2. All right. I'm not forgetting about that convenient x-intercept. Let's keep it there just so that we're perfect. And let's get this sketch going. All right, so we did not end up drawing the original graph here, but that's okay. It's not necessary. It's just it's useful if you want it. All right. Can you say in words? Let's go with pink. What this graph is doing? What this operation is doing?
Shifting to the right.
Shift. I'm going to say shift horizontally.
Okay.
But you are correct. Shift horizontally. Shift right in this example. So we have f of x minus h. I'm using these letters because these are letters that you use, everyone, when you did circles and hyperbolas and ellipses, and parabolas in geometry class. Right? You may remember that h takes you in the opposite direction. But x minus h, if h is positive, which in this case, is h positive?
H is positive because x minus 3 in our x minus h format, all you need to do is substitute in positive 3 and you'll get your h.
Yep. So if h is 3, we're going to have x minus h. Don't let that minus trick you. If h is positive, are we going left or right?
We are going right. I wonder if our heads are over this part of the window, Mr. Kirk.
Oh, yeah. Oh, I think you're totally right. And what I'm going to do, I'm so sorry, everyone. Can I select and drag? It doesn't seem so. I'm just going to write this real quick. So everyone, you've been hearing what we've been writing, but you haven't been seeing what we've been writing. So here it is again over here.
You can just scroll a little bit. I think it's okay.
I don't know if that's going to work though.
Oh no, just scroll down, scroll up so that the words go down.
You are. Let me go a little bit further just in case we're both stacked.
Oh yeah.
Yeah. It depends on if we're both talking or not.
But that was a vertical transformation that we did on the word. Boom.
Or was it a? Anyways, it is vertical regardless. Okay. So shift horizontal when x, we go right when h is positive, and we go left when h is negative, which is counterintuitive because in my mind, left in the Cartesian plane is negative. Wait, I think I've. Oh no, never mind. When h is positive, we go to the right, and when h is negative, we go to the left. Right? And this minus sign is going to mess us up sometimes.
The minus sign is confusing, yeah.
That's the part that confuses me.
But if you think about it in terms of this inequality that Mr. Kirk has set up, then the +3 comes out there of the shift in the positive 3 direction.
And I think Mrs. Contreras will agree that you should write this inequality whenever you're messing with stuff inside the function. All right, let's continue. All right. Let's go back to blue. I'm feeling Grover today. F of 2x.
Elmo. Come on.
F of 2x.
F of 2 times x. So that means that our inputs are all getting multiplied by 2.
Right? So think about it. What can you then plug into the function?
That means that what we can plug into the function is our interval divided by 2.
Right? Because if we plug in negative, if you think that this is making your the interval larger, like 2 might make you feel, 2 make it twice as big, you'd be wrong because you can't plug in -8, because if you plug in -8, you're going to get f of -16, which doesn't exist. We are on a restricted domain, as the title of this lesson indicates. Right? So you could realize that 2 makes it smaller intuitively, or let's get our inequality going. And let me get those equal signs before.
There you go.
We divide by 2 everywhere. And these are the new values. I almost forgot it again. These are the new values that you can plug in. When you plug in negative 2, you get f of negative 4, which we've now seen many times as 0. When you plug in negative 1, you get negative 2, which we've seen many times now is negative 2. When you plug in negative 1/3, you get negative 2/3, and f of negative 2/3 is 0. So f of e of 1/3 is 0. And I believe the last one's going to be 1/4.
Because it was 2/4, and now it's 1/4.
We have taken our check mark, and we've squeezed it in. We have done a what? What's the name of the transformation?
A horizontal dilation. No.
That's correct, right?
Yeah.
Yeah, dilation. I'm pretty sure I'm spelling dilation right. When I first started teaching this in Paris, I wrote it as dilation. And I wrote it for like an entire year incorrectly. No one ever called me on it because, like, I don't know. But I'm pretty sure I am correct this time with dilation.
That's cool. I actually don't know how to spell dilation, so I just learned that that's the correct spelling.
I'm pretty sure.
I'll tell my eye doctor that.
Yeah, exactly. But that's also how I taught dilations, because like your eye dilates.
Mm-hmm.
So it was definitely contradictory. Same with principal and principal. Yeah. Okay, math likes to mess with your understanding of language for sure. So
math is its own language.
So now I have f of, let's go bx. What does b when b is not positive? Sorry. When b is in between 0 and 1, what's happening?
So we're getting a squish.
Actually, we're about to figure this out. But yeah, we are switching. So we're jumping on G. Maybe we'll leave G for the person to do.
Okay.
So when B is between 0 and 1, we are, wait, say it again. You said squish?
I said squish, but you probably have a better word for it. Compress?
Wait, no, are we squishing? When B is between 0 and 1.
Oh, we're not. We're
Gotcha.
stretching.
Got him. It's a stretch. And I'm spelling stretch wrong again.
Stretch.
Yeah. And when B is larger than 1, we're going to
compress. Squish.
Compress. Yeah.
Smush.
I believe compress is what most textbooks will use, but smush, squish, those are more fun. So I encourage those. Don't let the man tell you what to do. All right, so we're gonna leave G for you guys to do. All right, think about what values you can plug in so that F will accept it. Right? What values can you plug into G so that when you divide that number by 2, it's between -4 and 2. All right. Here's the answer. It is going to be -8, 0. It's going to be 4/3. Yeah, 4/3, 0. -4/3, 0. We're gonna have -2, I believe -4, -2, and a 4, 4.
Wow. So big.
Yeah. You're stretching.
It's a really lazy check.
It's like when you're grading really fast and you go, "Woo, good job."
Yep, I do that a lot.
Yeah, me too. Not my proudest moment. All right, we got some more transformations for you. All right, the ones that are inside the function are a little bit more counterintuitive, so we want to think about them in intense detail. Here we are at H. There's your check mark on the left and hand to the side for reference. All right, what values can we plug into this?
Well, f of -x means that all of our domain needs to still work from -4 to +2.
Mm-hmm.
So are we going from -2 to +4?
I believe so, right? Because when you plug in 4 now into H, F says, okay, well, I have -4, and we know what that is. That's 0. So H of 4 is 0. Right? Give me some more. Give me some more points. Give me F of H of 2.
H of 2 is going to be -2.
F of -2, which ends up being -2. So H of 2 is -2. And then I think the last one here we care about is 2. No.
Well, h of 2/3 is f of negative 2/3, which is 0.
And then h of negative 2.
H of negative 2 is f of positive 2, which is 4.
Awesome. I believe there we go.
You just, you just took that check and you turned it around.
A little switchy.
Switchy, switchy. Is that what we're calling it?
Yeah, we'll call it switchy. All right. Fun fact though, you didn't need to do all this thinking because I'm telling you guys. I'll leave the top one. All right. If you write this as an inequality, that should be that's a negative 4, negative x, and then 2. And you solve this thing. What do I need to do to solve this for x?
Divide by -1 everywhere, but since we're dividing by a negative with an inequality, we gotta flip all our signs like responsible mathematicians.
Would you look at that? Boom. That's our domain.
Hey.
Okay. But when you have a negative in front of your input value, that is going to be a reflection over the y-axis. X equals 0. Cool.
Cool.
There you go.
Very empowering.
How so?
I don't know. I think that like being able to think of the picture in terms of the like a change in something in the function, just like that's a connection that's really nice.
Mm-hmm. I am a very visual learner. That is just who I am, and I know not everyone's like that. Right? I sympathize with people that are not. Doing these transformations is tricky, and right now we're doing them one at a time. In a minute, more than a minute, we're gonna do them all at the same time, and we need to like figure out which one happens first. Keep it all in our head. It is not easy. Keep that in mind, everyone. Right? We can make these quite difficult. So, that's a good thing. Difficult is good. Difficult is not a bad thing. If you look at difficulty and you shut down, our job as teachers is to squash that feeling and make you feel empowered, as Mrs. Contreras is saying. So this is difficult, especially if you're not a visual person. So don't fret if this is difficult right now. Here we go. I love the absolute value transformations. These are non-conventional. They are not really rigid or non-rigid transformations. They are their own like side quest thing.
Side quest.
I don't know why I said that. That's what I call. So I have quizzes and tests, right? So something that's like more than a quiz, but not as much as a test, that's a quest. But something that's like more than a quiz, but less than a quest, that's a side quest.
Oh my goodness.
Every now and then I have a side quest, yeah.
Such a gamer, Mr. Kirk.
I'm playing this game. Oh, no, I'm not gonna, this video would be super long if I start ranting about video games. Let's get back to where we were. The absolute value function. Now, this one's a little bit more difficult to deal with. And I still have a hard time conceptualizing. And the best way to do this one, I think, is not necessarily with an inequality. I mean, you can. Let me not forget that. I want to get yelled at. You can think about it with an inequality, but what I'd rather do is just plug some stuff in. Let's figure out what this transformation does and then put it in the pocket for later.
So
what can I plug into this thing?
I mean, like we can plug in 0. That's pretty safe because then the absolute value doesn't change it.
Yeah, so, and it's going to be the same thing. So I believe that's been 1 this entire time.
Okay. That's good.
What?
We got an
anchor. I'm plugging to all the positive numbers, right? Are not going to get changed.
Oh, yeah, that's true.
F of 0, F of 1, F of 2, they're all going to be the same. So let me just get that F of 2, 4. Right? The absolute value doesn't change the positive stuff. That we know.
When we plug in negative 2/3, right? Because that was our x-intercept. Then we get
so
f of.
Intuitively, we think maybe that's going to be 0 stuff. But that becomes f of positive 2/3, right?
And that is all of a sudden something else.
That I believe is 2.
because it was 3/2 times 2/3, which is
That's
1,
1.
plus 1 is 2.
Yeah. Cool. So negative 2/3. What happens when I plug in -2?
Plug in -2, you get f of positive 2, which is, we have it on our graph already. That's, what is that? 4?
4.
Yeah.
All right, so it's doing this. Is it going to keep going? Is this check mark getting like reflected and shot up?
I don't
What happens
know.
when I plug in -4?
If you plug in -4, then you get f of positive 4, which
That's
is
undefined, right?
undefined because we have a restricted domain.
Yeah, that doesn't exist with this function. This function is
Mhm.
only defined from -4 to 2. What if I plug in f of -2.000000004?
Then you're taking the absolute value of that, right? So it's f of slightly more than 2, which
F
is,
of 2.000000004.
are you sure this is the right amount of zeros? I don't know. Does it matter? I don't think it matters. Oh my gosh, you're counting. Okay.
It is the right amount of zeros. Thank
Wow.
you.
Wild. So
It's not wild. It was intention. Okay.
so that's also undefined because our domain only goes up to positive 2.
So I believe we're done then, right? We get like this v function. This person that like set out to draw a check mark but failed. It's like when you draw a check mark but you accidentally like start too high up. I digress. Sometimes jokes aren't funny.
Ooh, do you want to hear a funny joke?
I do.
How many tickles does it take to make an octopus laugh?
I'm just. How many tickles does it take to make an octopus laugh? I'm just gonna go out on a whim and say 8.
No, 10 tickles.
Oh boy, that was almost as bad as my joke that wasn't funny at all.
But you laughed, so you know.
Yeah, you're right. I'm just trying to make myself feel better. All right. So this is our function. Can we describe this in words? What we've just done.
Oh my god.
Let me graph real quick the original function in blue.
The OG check.
The OG check. All right, we're gonna get reamed out for that one. We're not hip enough to,
We're not
Anyways.
hip enough. I know what TikTok lights are now. Like, come on, Mr. Kirk. I'm hip.
All right, so the blue is the original. Red is the authentic Elmo final answer.
So it just looks like that positive part. The positive part of the check with the positive domain part just got reflected, and the rest of the check just went away. It just got sprinkled with some disappearing dust.
That stuff is negative. Like the negative domain is gone now. Gone, out of here.
Boom.
The positive domain is now doubled. So let's put this thing into words. Let's see if I can get this. Oh, I don't want that. There we go. Whatever. Let's get this thing into words. What does the absolute value function do?
Delete the negative domain and reflect the positive domain across the vertical axis.
Delete the negative domain and then reflect the positive domain?
Yes.
Were we successful?
No, I don't think so.
No.
Delete the negative. Yeah, that's 6.
Oh, wait, I got you.
Delete negative domain, reflect the, that's 5.
No.
Positive. And then you need another line.
No. So if Precalc, if you didn't notice, we're trying to get a haiku here. Darn it. We were so ready too.
I should have written
Delete
it down.
negative domain. Reflect. Let's just proceed.
Let's just let the students, if the students can write haikus for each of these transformations, like in words on their classwork, you get to choose a theme for an upcoming video, because this one is clearly just bad jokes and talking about Sesame Street.
Yeah. So let's get a better theme for next time from you guys. But you only get we can't just have everyone suggest stuff because that would be too much. If you could earn it, we want some haikus for transformations that we can keep in our pockets for future years of teaching.
And so that we can see how creative you are, because that's wonderful.
That's true. It was definitely for me a like selfish, like I want these for the future. But you bring up a good point. This is creativity important. All right. The absolute value outside the function. We just messed with inside the function, the domain. All these past like 6 transformations, 1, 2, 3, 4, 5 transformations have all been domain changes. We're back to range changes.
Range change.
Range change.
So we got the check, and we have part of it that has outputs that are negative, and those are going to change with this absolute value. But I think the positive part, which we had reflected in the previous one, I think that one doesn't change at all.
Right, yeah, because so this is positive, right?
Yeah.
Right? Am I missing anything?
Well, I think that there actually is like a little smidgen part from negative 2/3 to, yeah, there you go.
So when you say positive, you don't mean the positive domain.
Mm,
You mean the positive range.
that's true, yes.
So you kind of like scan the x-axis, and this whenever you have values above that line, you leave them be.
It's like what's above the horizon, or what's above ground.
Air.
Well, like all of that red part is above ground, but then all the blue part that's still visible, that's all below ground.
It's like earth and water.
Wow.
All right, so all
We
these
have an Avatar theme. Okay.
I know, I was thinking the same thing. All right, wait. What do I do with this blue?
With a blue, I think you need to reflect it up.
Okay. Anything, all these negative range values, they don't get deleted. Right? We can still. There's no restrictions on the range. In I, we had restrictions on the domain. We like ran into problems when we plugged in 2.00000000004. When we plug those things in, that was the right amount of zeros, by the way, 9. But when we're dealing with the range, it's okay. Right? So what we're doing in this one is we are leaving the positive range, not domain. Right? We can have positive stuff in the negative domain. All the positive range values stay put. And then we do a little whoosh, flip for the other stuff. So how can we put this into words? We can try to haiku it.
Negative range part.
Negative range part.
Reflect
Flip.
over the
Flippy.
flippy
Up. Flippy up.
over.
Up and up.
Up and up.
Flippy up and, is that right?
Flippy up and up. Yeah.
Yeah. And then
Nothing below ground.
nothing below ground? Above ground.
Nothing below ground. There's nothing below the x-axis.
But wait, I was referring to how we don't do anything to anything above the ground, right? We flippy the negative stuff.
No change above ground.
No change above ground. Boom. All right, above ground, not left and right of the y-axis. These are the most difficult ones, I think, in my opinion. Are these absolute values ones? Because we don't have like a prior knowledge on these. We have dilations, we have rigid transformations from geometry, but these are coming out of nowhere, left field. All right, I referenced it earlier. Mrs. Contreras, how are we doing on time for you?
I think we have 10 minutes, so.
All right, cool. We might be able to knock this thing out. Let's do it. All right, we have multiple transformations happening. Now, they don't happen all at the exact same time. All right, we have an order of operations for transformation.
Is it PEMDAS?
But it's not PEMDAS. We need to be really careful. Because I like to think about, imagine you're Frodo Baggins. and the journey to Mordor is a function. What do you do first?
First, I pick up the ring and then offer it to Gandalf.
Yeah. And Gandalf, say no.
Okay, right. And then after that, I watch my friend get, tackled by Gandalf and then pulled in from the window.
All
His
right.
name is Samwise. The second thing I do.
I think that if we recite the entire plot of The Lord of the Rings
From memory, as one
from
does.
memory, which I know we could do, don't get me wrong, we're going to be here longer than 10 minutes.
That's
So
fair.
let's just now think about if I send a number on the function k's journey. So let's say I plug in, what do you think Frodo's favorite number is? Make sure it's
What?
Make sure it's in the domain.
Oh, it's probably 1 because of one ring to hold them all.
So I'm going to do negative 1.
There.
So what happens to this negative 1? What happens first?
Negative 1 gets 3 added to it.
Let me put this 2 here. And then so we have 3 added to it.
So then we get f of 2. And that's
so
still in our domain.
Let's freeze. We just added 3. What does that 3 do to our check mark?
That takes a horizontal translation to the left. Wait, did I do
So
that?
I'm gonna say translation. It's positive, so we're going in the negative direction. Left 3 units. Right? That's the first thing that happened to Frodo and his favorite number, negative 1. That's the first thing that happens. Then the 2 hits the function, right? Frodo throws that ring into the fire, right? They got on the Eagles, and the Eagles took them there without any problem.
Wow, spoilers, Mr. Kirk.
That is what should have happened. So f of 2, the function evaluates 2, which gives us 4, and 4 hits it with a 2, that's
8.
Right, so we end up getting 8. So we plugged in negative 1, we get 8. I'm not going to do this for all the points, though, because all this was meant to do was to exemplify what happens first. The check mark moves to the left. I'm not sure if this is left for you guys or not. Right? It moves to the left 3, then dilates by 2 away from the x-axis. That's what the 2 does. So I'm just going to take all my values and do that at once. All right, so I had negative 4, 0. That's going to get shifted 3. That happens first. And then 0 dilated 2 is still 0. The negative 2 gets moved 3. It goes to negative 4. And then the negative 2/3 goes to, and then you multiply by 0. I'm not going to say the number. I don't feel like dealing with those big fractions. I just need to do
That point.
Yeah. And then we are done. All right, that's the goal here. To look at a function and then know what it looks like simply by the parent function and what transformations are happening. All right, when you leave this course, you will be able to look at any graph and know what it looks like, or spend 30 seconds sketching it out and then knowing what it looks like. So let me proceed. That's what. So to kind of talk about what we just did. Recap. We do what's inside the function before we do what's outside the function. Negative 2 for x plus 4. What do we do here first?
The first thing that we do is we just have a function. We have our function evaluated somewhere, and then
so our domain doesn't change.
Our domain doesn't change.
So once it's evaluated, what happens next to whatever point we plug in?
I think that we have it's a negative 2, so there's a reflection happening and there's a dilation happening.
Mm-hmm. So, and we can kind of do those at the same time. To make matters simple and not provide too much explanation, but you feel free to look and see why we can do those at the same time. They don't affect each other in a nutshell. Right? If I did this 4 first and then dilated, that would end up with a different result if I did the 2 first and then the 4. But the negative 2 and the negative 1 and the 2 do kind of are simultaneous.
Is it because multiplication is commutative?
That's a really good point. I think so. I think that's a really good point. I've never thought about it that way. You've just increased my knowledge. Thank you.
Just
All right, so
wondering,
the second step.
that's
go
up 4. Yeah.
I'm gonna say -2 dilation. Okay? And if you think back to geometry, by the way, -2 dilation, that is a dilation. It's both a reflection and I'm not gonna get into the semantics of dilations and dilation centers and stuff like that. But this goes up 4. So this is the order that we do it. So we're gonna take our check mark, and I'm gonna go ahead and draw in blue in the Grover color. And that is a Grover blue too.
The OG
I said that
function.
earlier, and I didn't give you enough credit for that is a Grover blue. Like, I'm gonna pause it real quick. That is Grover blue, and you know what? You couldn't be more right. Like, that is Grover blue. Look at that.
Hello, everybody.
That's what it said. You said you practiced your Grover.
This is a check mark.
Should we do an entire video in Sesame Street impression?
Yes.
It's a big no from me. All right. So that's our Grover blue. We do the -2 first, which means both a reflection over the x-axis, because we're outside the function, we're changing the range, and then multiply by 2. So that's going to go there. Oh, let me not put it there. You know what I'm going to do? This is also very valid. I'm going to do the 2 steps separately, and then have a final answer. What am I missing here? Oh, I need to, this needs to be -8, right?
-8.
Yep, and then this needs to be -2. All right, that's the first transformation, the -2. And then the 4, up 4, I'm going to do the final one in Elmo red. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Sweet.
Nice.
All right, so that final answer. And students, if you want to break it up into increments, that is totally fine. All right, and we suggest, I know you got colored pencils somewhere in your house. Break them out for this lesson, and for when we do this in class.
Or just crayons. Crayons work too.
Crayons too, but colored pencils are better. Finer tip.
Or if you have cool Muji pens, it's also.
All right, so this last one, and we can make these as complicated as we want, but just to recap, we do the inside before the outside. That's what K represents. Here, we do it when we're on the outside. First, we do what's being multiplied to the function. Then we do what's being added to the function. All right? We kind of do go through PEMDAS, or the normal order of operations. But things are different over here in my M function. F of 1/2 x plus 1. And this is where the inequality just gives you all the answers. It reveals what happens. When you're dealing on the inside of a function and you want to know what happens first, when you want to know the order of transformations, give yourself that inequality. Here we need to be between -4 and 2. And we're going to solve this inequality. And in solving this inequality, it is going to tell us the steps. What do we do first?
Subtract 1.
Subtract 1. I am going to write down over here, the shift is first. And that's a shift to the left.
Slide to the left.
All right, and this is also telling us that it's to the left. We're subtracting 1. We're going to the negative direction. And then we have 1/2 x, and let's see, you can see that all right? Even
yeah,
though
that looks
I'm
good.
bleeding into, okay, cool.
Although I am concerned that your shift left, like those steps might be.
Oh, I did it again.
Not visible.
So I wrote shift left over here. And then what happens next?
And then we'll multiply by 2 everywhere. And since that doesn't change your signs, you don't have to do anything with your inequalities. So you got a new domain of -10 to 2, which is bigger. So you have a horizontal dilation.
Yeah, and if you want to check, you can just plug in -10. If I plug in -10, I get -5 plus 1, -4. F is okay with -4. And it gives me 0.
Pause.
I
gotta go.
All right.
Sorry.
Okay, we're back. And just so everyone knows, we had to stop because of math help. Don't forget that there is math help between 2:45 and 3:15 on what days, Mrs. Contreras?
On B days.
Awesome. Take advantage of that. Mrs. Contreras, you were there. I was not there today, but believe there's a rotation, right?
Well, Mrs. Strata and I are there, and then any other teachers who want to come, and also Math Honor Society tutors.
Sweet. All right, so I will be there with Ms. Contreras sometimes, and we'll be hanging out, and you get help from your peers. This is awesome. All right, we'll finish this video out with this last translation. Sorry about that, everyone. We plugged in -10 because that is a valid value in our domain of m, because after doing all these transformations, it becomes -4, which is valid. Right, 2 was the furthest point that we could plug in on the right, our most positive value, or our most to the right on the number line value. Plug in 2, we get 2 divided by 2, 1 plus 1 is 1. F can accept 1, and I believe we get 4 when we do that.
1 plus 1 is 2.
F of 2 is 4.
F
1
of
plus
2
1
is
is
4. Okay.
right?
Yeah. I think you said 1 plus 1 is 1, and that's not a thing.
Well, if you do one of these things, like, well, no, it's still 2. Never mind. All right. All right. So, but the point of this whole lesson is not that you just point plot things. I don't want to give you a complicated graph like I don't know, 2 times x plus 1 squared divided by 3 plus 1. I don't want to give you that, and then you just plot points. I want you to take advantage of this understanding of transformations. I want you to know that you shift to the left 1. Then you dilate by 2/3. Then you add 1. So we want to understand what's happening here. Oh, we have a guest. We have a guest. Come and say hi to Mrs. Crabtree's math classes.
Hello, everyone.
This is Mr. Crabtree. He is one of the stage crew sponsors. Are we going to finish this?
He's really great.
Okay.
He is really great.
You can start off.
All right. So sorry about that, everyone. All right. So what's happening here, Mrs. Contreras? What's happening in this transformation?
There's a shift left and there's a dilate horizontally. So we just need our check.
Yep. I'm going to go ahead and put it here. Let me go ahead and put it in blue, in Grover blue. Boom. Boom. That might be my new favorite color. You know, one of my icebreakers recently was, what's your favorite color?
Oh.
And I just like the idea of my favorite color being Grover blue. That should be a Crayola color. Anyways, we're going to take this check mark. We're going to move it to the left 1, and then take all those new values, the horizontal values, and dilate them by 2. All right. So this point goes to -5 and then to -10. This one goes to -3 and then to -6. And let's get that in Elmo red. All right, this point up here goes to, this is going to go in the, it's going to go to the left, but then go back to the right because it's being stretched in the positive direction by a scale factor of 2. And I guess we can get this one too. It's going to go there. And then what is 4/3? Yeah, no, there. Yeah, what is 4/3 times 2? 8/3.
4/3 times 2 is 8/3.
4, 5, 6, 7, 8. It's going to go right there.
It's almost 3. Yeah.
And then if, you know what, let's take advantage of the powers of Kami. Where is my shape? There's my line. It is red. And there. I think I might have done something wrong.
Huh.
If you can figure out what I've done wrong, then let us know. But I think I might have done something wrong, but we're not going to dig into it right now.
Exercise for the viewer.
Yeah. Oh well. So, I know what I did wrong. I forgot to shift. So we'll ask a question, and then we'll reveal the answer. I didn't shift and then multiply by 2. So really it's 2/3. 2/3, it's going to be 5/3 times 2, 10/3. 10/3. -10/3. All right, there it is. There's our check, but we shifted and then dilated. And then just to recap this lesson, we have tons of different transformations. We have transformations, dilations, reflections. Right? We have those transformations to the domain and the range, and they're different. Right? When we're working inside the domain, it's counterintuitive. It's the opposite of what we're saying. Right? If there's a 3 there, a -3 there, we're going in the positive direction, not negative direction. Right? Same thing with these. If there's a 2 there, we're getting smaller. If there's a 1/2, we're getting bigger. And then we can do all of these things. Some absolute value stuff. That was tricky. We can do all of these things in succession, and knowing the order matters. Right? If you did this one in the opposite direction, if you did the 1/2 then the 1, you wouldn't have got what we've drawn in red. So be very careful. Knowing the order is important. And these inequalities, ooh. These inequalities are really important. And not really important, but really useful. I think that's where we're going to stop. Got any words of wisdom for everyone?
Drink water.
Drink water. Drink water. I like that. I have coffee. Not the
It's not water.
it's not water. Is this a diuretic?
It is.
Yeah. That means that it makes you dehydrated, right?
Yep.
Yeah.
And,
Well,
other things that sound like diuretic.
true. Maybe that's.
Drink
We'll
water.
leave it there. Let's go ahead and close this one out before we say anything that will embarrass us. See ya.
All right. Wait, we didn't stop the screen share, so it was just a little.
Oh. See ya.